Hello, cosmic travelers, welcome. We're about to embark on a journey into one of the universe's greatest mysteries, gravity. It's the silent, invisible force that shapes our cosmos, keeping your feet on the ground, holding Earth in orbit, and gathering gas and dust to form stars and galaxies. But what is gravity, really? Is it just a force pulling us down, or is there something much stranger going on? Imagine a universe without gravity. Planets would drift away, stars wouldn't form, and life as we know it would be impossible. Gravity is the grand architect of the cosmos, the cosmic glue holding everything together. For centuries we thought we understood it, a simple pull between objects with mass. But the deeper we look, the more mysterious gravity becomes. This is a story of brilliant minds and mind-bending ideas, a quest that continues to this day. Our journey will take us from a falling apple to the edge of black holes, from the familiar world of our solar system to the bizarre realm of quantum mechanics. We'll explore questions that challenge our very perception of space and time. Is the universe a symphony of vibrating strings? Is space-time made of tiny, indivisible loops? These are questions about the fundamental nature of reality, questions that connect us all to the grand cosmic story. The story of gravity is the story of our own understanding, a testament to human curiosity. We look up at the stars and wonder. We drop a stone and ask why. This desire to know has led us from simple observations to profound theories that have reshaped our world. So fasten your seatbelts. The ship of the imagination is ready. Our first stop, the mind of a genius who saw the universe in a falling apple. The adventure has just begun. Our story begins in 17th century England, where Isaac Newton sat under an apple tree thinking. He saw an apple fall, a simple event, but Newton saw a connection between that apple and the moon in the sky. He wondered, could the same force pulling the apple down also hold the moon in orbit? Before Newton, people believed the heavens and earth followed different rules. Newton's insight was revolutionary. The laws of nature are universal. The same force governs the fall of an apple and the orbit of a planet, gravity. He gave us the law of universal gravitation, predicting planetary motion with incredible accuracy. Newton's law described gravity as a force of attraction between any two objects with mass. The more massive the objects, the stronger the pull, the farther apart, the weaker. For over 2 centuries, Newton's gravity reigned supreme, allowing us to predict eclipses, discover new planets, and send probes into space. But even Newton was troubled. He could describe how gravity worked, but not why. How did the sun reach across empty space to pull on the Earth? He called it action at a distance, but had no explanation for the mechanism. It was a puzzle left for future generations. A new kind of thinker was needed, someone who could see the universe in a completely new way. Fast forward to the early 20th century, enter Albert Einstein. Einstein wasn't satisfied with Newton's action at a distance. He spent years reimagining gravity, space, and time. His breakthrough space and time are woven together into a single 4-dimensional fabric, spacetime. Massive objects like the sun warp and curve this fabric. Imagine placing a heavy ball on a stretched rubber sheet. The sheet curves under the weight. In Einstein's view, gravity isn't a force at all. The Earth isn't being pulled by the sun, it's following the straightest possible path through curved spacetime. This was the general theory of relativity. Gravity is the geometry of spacetime itself. Time itself is affected by gravity. Clocks tick slower in stronger gravitational fields. This isn't just theory. GPS satellites must account for this effect, or your navigation would be miles off. Einstein's gravity is woven into the technology of our modern world. So, we have 2 pictures of gravity, Newton's force, and Einstein's curved spacetime. For everyday life, Newton's view works, but on cosmic scales or near black holes, Einstein's picture matches reality. Einstein's theory predicted black holes, regions where gravity is so intense that nothing, not even light, can escape. But is gravity a fundamental force or something else? Some physicists propose gravity is emergent, like temperature, a property that arises from the collective behavior of smaller parts. This entropic gravity suggests gravity emerges from the universe's tendency toward disorder or entropy. In this view, space-time and gravity are patterns emerging from a deeper reality. It's a radical idea challenging everything we thought we knew. Now let's shrink down to the quantum realm, the world of atoms and subatomic particles. Here, particles can be in multiple places at once, popping in and out of existence. Quantum mechanics governs this world, and it's incredibly successful. Powering everything from computers to lasers, we have two amazing theories: Einstein's general relativity for the very large and quantum mechanics for the very small. Both work perfectly in their domains, but they don't work together. When you try to combine them, the math breaks down, especially in extreme situations like black holes or the Big Bang. To understand these cosmic events, we need a theory that unites gravity with the quantum world, a theory of quantum gravity. This is the biggest challenge in physics today. Why is it so hard? Einstein's gravity is smooth and continuous, but the quantum world is chunky and discrete. Is space-time itself made of tiny, indivisible units? Finding quantum gravity means discovering the source code of the cosmos. The quest for quantum gravity is part of a grander dream, a theory of everything. We know four fundamental forces: gravity, the strong and weak nuclear forces, and electromagnetism. Physicists have unified the weak force and electromagnetism into the electro-weak force, a monumental achievement. The next step is a grand unified theory, merging the strong force with the electro-weak. But gravity remains the odd one out, far weaker than the others. Why is gravity so weak? This hierarchy problem is a major puzzle. A theory of everything would explain this and show how all four forces arise from a single source. Imagine a single equation describing all phenomena, from the Big Bang to the fate of the cosmos. The search continues, driven by curiosity and the hope of ultimate understanding. What are the leading candidates for quantum gravity? One is string theory. It proposes that the universe's fundamental building blocks are tiny, vibrating strings of energy. Different vibration patterns create different particles and forces, including gravity. The universe in this view is a cosmic symphony played on infinitesimal strings. But string theory requires extra dimensions, 10 or 11 in total, curled up so small we can't see them. It's mathematically beautiful and naturally includes gravity, but there's a catch. String theory hasn't made a single testable prediction yet. The energies needed are far beyond our reach. Some scientists are skeptical, calling it more philosophy than science. The jury is still out on the cosmic symphony. Another contender is loop quantum gravity, which takes a different approach. Instead of starting with particles, it applies quantum rules directly to space-time. It suggests space-time is not smooth, but made of discrete, indivisible loops, a woven network. Think of fabric. From afar, it looks smooth, but up close, it's threads. Loop quantum gravity says there's a smallest possible unit of area and volume. This quantum foam constantly fluctuates at the tiniest scale. Space and time, in this view, emerge from the relationships within this quantum network. It avoids the singularity at a black hole's center, suggesting matter is compressed to a finite state. Some versions even propose our universe emerged from a previous one, a big bounce. Like string theory, it's a work in progress, and testing its predictions is a huge challenge. So, where does that leave us? We've journeyed from Newton's force to Einstein's curved space-time and into the quantum world. The true nature of gravity remains one of science's deepest mysteries. Is it a force, geometry, an emergent property, or something else entirely? The quest to understand gravity is a quest to understand our origins and fate. A complete theory would unlock the secrets of the Big Bang and black holes, and might even explain dark matter and dark energy. Science builds models, Newton's, then Einstein's, each revealing deeper puzzles. Every answer leads to more profound questions. The universe isn't obligated to make sense to us, but we're compelled to try. We look into the darkness not just to see the stars, but to understand them. The mystery of gravity reminds us we're still at the beginning of our exploration. Vast oceans of knowledge remain, and the journey itself is the greatest adventure of all.